Now that we've solved this entire forced harmonic oscillator by hand and written it in a very cool way using some complexification, we're going to convert it to a system so we can actually look at a phase portrait. And remember, phase portraits for non-autonomous differential equations or for systems are going to be more complicated, so we're not going to be making them by hand, but we will look at some approximations generated from a computer. So before doing that, let's convert our good old differential equation that we did in the last example to a system. So this was our differential equation for cosine of 2t. How does this convert to a system? Well, we are going to let v be y dot. Then v dot, of course, is y double prime. And if we solve for y double dot, we subtract everything over. V dot will be negative 10y minus 2y dot, which we'll call y dot v, plus 4 cosine of 2t. And we can rewrite this as dy dt is equal to some matrix, which is going to be very similar, 0, 1, right, because y dot is just v, negative 10, negative 2, times y, which we'll call y and v, plus, right, now there's a part that's not like a linear coefficient for y and v. This is just something that only depends on the independent variable. And notice that y dot doesn't depend on this at all. It's only y double dot that does. So we'll have 4 cosine of 2t, like so. This is how we would write this as a non-homogeneous system of first order differential equations. And this is still our matrix A. And analysis of eigenvalues will still lead us to straight line solutions for the homogeneous version. But, and of course, these have complex eigenvalues anyway, so there won't be any straight line solutions. But we're not going to be doing much with phase portraits on this by hand. But we can look at some pictures generated by technology. So let's start by looking at this picture up here on the left. Now notice right off the bat, we see two things that we have not seen in all of chapter 3. Not really. Here we have an initial condition that says we are starting completely at rest. This is a forced harmonic oscillator with sinusoidal forcing function. So think about this as a spring that is being that has a sinusoidal force being applied to the object. So maybe it's a spring on a table and we're either shaking the table in periodic motion or tilting the table in periodic motion. This initial condition, y is initially 0. This is spring is initially at rest. And v is initially 0 as well. This is completely at rest. But the table is not at rest. So even though it starts completely at rest, usually that's an equilibrium. Usually if something starts at rest, it stays at rest. Usually 0, 0 is our equilibrium. But not anymore. We're not homogeneous anymore. 0, 0 is not always an equilibrium anymore. And it's certainly not an equilibrium now. If you're at rest and the table's going bananas, you start going bananas too. So we can see that we start at 0, 0, which is not an equilibrium. And then we kind of go here and, oh my gosh, look at this. What happens here? Remember, this is non-autonomous, so it's fine that it looks like it crosses because really this phase portrait doesn't really exist in the YV plane. It really exists in YVT space. So we're just like looking down on this, and T is the third dimension coming towards us. So yeah. So it's not actually crossing because these are at different times. So we see this and it goes out and it goes in, and then it kind of, you can see it kind of turns into an ellipse in the phase portrait for that initial condition, which makes sense because we know our solution has a natural response that looks like underdamped harmonic oscillator, but a forced response that's periodic motion. And we can see that if we plot the solution, this is just the position. We're not plotting the velocity, just the position y over time. Yeah, it starts and like kind of spirals out in a sense, but then it really gets pretty steady. Eventually, the forced response is just going to take over. And again, I cannot stress enough that this forced response, which is, you know, the steady state solution, is not the same as the forcing function. The forcing function is 4 cosine of 2t. This is not 4 cosine of 2t. It's related, it'll have the same period, but it'll have a different amplitude and it'll have a phase shift. Okay. Oh, I just realized I never showed something very cool from an earlier section. I kind of forgot. But when we found the general solution for one of our forcing functions, I just really wanted to show real quickly that no matter what your initial conditions are, for a forced harmonic oscillator, eventually you just match the forcing function. So this is the first example that we did in this section, in this section. And eventually we just become that blue forced response. Okay. But I forgot to show that. Okay, so that initial condition leads to that behavior. What if our initial condition was pretty big? Right? What if we start off 2 units away from the origin, but again with no initial velocity? Well, then it turns out, right, we're going to get sucked back to equilibrium quite quickly. And then we'll bounce a little bit, but eventually we're still going to get into that same forced response. And it looks a little different, right? This looks like an ellipse. This doesn't look like an ellipse, but this actually is an ellipse. The second one, this is an ellipse. Why? Look at the scale, right? 1 is this big on the vertical axis and 1 is this big on the horizontal axis. So kind of looks like a circle, but really it's an ellipse, right? It goes up a little bit more than 1 and it goes to the right around a half, which is exactly what we had with this ellipse over here. So even with a different initial condition, you're going to see from a different perspective that it has the same forced response. And again, you can see that if you plot the solution over time, here we started at 0 in our position. Here we started at 2 at our position. And quite quickly, right, we lose that speed because we have an underdamped harmonic oscillator. All harmonic oscillators, if there's any damping, are going to lose that speed. And they're eventually going to 0, but here there's a forcing function, so we're not actually going to 0. And we'll see that same forcing function. Do you believe me? Let's look at this point. It's a little after 2 pi, and it's at an amplitude of a little bit more than 0.5. Look at this point. A little bit after 2 pi, and height, not amplitude. Well, in this case, they're the same. A little bit more than 0.5. So we start at very different situations. You can have 2 springs on this table. One spring started fully extended, and the other spring starting at rest. Eventually, both springs are just going to match the groove, as long as they have the same spring and the same mass. They're going to match the groove of the table or the earthquake. All right. Those are the main things that I wanted to talk about for these figures. Oh yeah, one more thing is this one's really quite obvious, that it starts off looking like a spiral, that underdamped harmonic oscillator, because our initial condition was so big that the forced response was dominated by the natural response. If this is our solution, if our initial condition's big enough, then initially this will dominate. If K1 and K2 are really big, this is going to be relatively small. But these are exponentially decaying. So it doesn't matter how big K1 and K2 are, eventually they go away. That's kind of how it all ties together. All right, let's look at another figure, and this is what we're going to end the section with. So here, really kind of, these graphs are intended to really drive that point home of where you start has a very big difference on how you get to that steady state behavior. And both of these get to the same ellipse, that same steady state behavior. And this one doesn't look like it, but it's because we're really zoomed out, right? But there really is like a little ellipse right here that all of these are going towards. So if we have big initial conditions, and here I've plotted 4 different initial conditions. I didn't. I took this from the book. The book plotted 4 different initial conditions, and they are all spiraling towards the origin. It kind of actually looks more like the critically damped case here. So I did double check that this is not critically damped. And we can quickly double check by looking at the trace determinant plane. What's the trace of this matrix? It's -2. What's the determinant of this matrix? It's +10. So if we pulled up the trace determinant plane, well, -2 trace is over here. 10 as a determinant, well, I don't know, that's above 5, right? It's definitely underdamped. Definitely going to see this spiral behavior. And indeed, right, if we look over here, it does look like that, right? We are spiraling very similarly. And again, the determinant should be bigger. This calculator is just more for playing around. This is what it would look like if the determinant were smaller. But as the determinant gets bigger, it gets more and more spirally, and it will look more similar to what we have. Okay. And conversely, right, this is a big initial condition, because our restoring and damping forces are proportional to the position and velocity respectively. The restoring force, the force of the spring pulling you back to equilibrium, is proportional to how far you are from equilibrium. That was Hooke's law, right? Force is kx or -kx, depending on how you're defining your constant. It's proportional to the position. Whereas, again, we're saying the damping force, which we introduced, was proportional to the velocity. Okay? So, of course, you know, those forces are going to be really big when our initial conditions are very big. And that force is going to be way more than that little table tilt, right? If you got a spring that's been like launched into in outer space, then like a little table shifting, it's really not going to do much until that spring has kind of done its thing. But on the other hand, right, if again we have 2 different smaller initial conditions, here again we're plotting that initial condition where we start at rest completely. No positions at equilibrium, velocity is 0. And here's another initial condition for a different initial condition where we start with a position and velocity both equal to like +1, I think. Okay, and you can see if we have smaller initial conditions, well, then originally we have smaller restoring and damping forces, then that external force, that forcing function, really dominates much quicker. And again, this is really the same ellipse as this. Just look at your axes. We're very zoomed in over here on the right. That's pretty much it. Cool stuff. I love qualitative analysis. Love the trace determinant plane. Love looking at phase portraits. One more reminder again, because this is non-autonomous, 0 is not an equilibrium. That table's moving. And it's okay that they cross, in quotes, each other, because it's at different times. This is non-autonomous anymore. They're different times. That's pretty much it. Hope you enjoyed this sinusoidal forcing. Hope you enjoyed the complex analysis. I should comment, and I was going to do this earlier, Appendix C in our textbook has more information on complex analysis. So if you want more review over the complex plane, over polar form of complex numbers, please look that up because we only covered it very, very briefly. It's also in many other places on the internet, so you could also look there. But that's pretty much it. The next section, remember, we're going back to undamped harmonic oscillators. And we're going to say, what does sinusoidal forcing look like there? And we'll tie it into something really cool called resonance. Should be great. Hope you enjoy. Have a good rest of your day. Bye-bye.